Bismillahirrahmanirrahim. Dear student, I'll start lecture number 1 for week number 13. If you recall, in the last lecture we discussed two important families of continuous random variables. First was the continuous uniform distribution, continuous uniform random variable. The second was the exponential distribution or the exponential random variable. Now we'll in today's lecture discuss the third and perhaps the most important of the random variables in this course, and that is Gaussian random variable. This variable and this distribution is so common, so normal in science, in statistics, that it is also called normal distribution as well, because it occurs so normally. First, let me write the definition of this Gaussian random variable. We say x is a Gaussian random variable if the PDF of x is f sub x of x, and that is equal to 1 over 2 pi sigma square all under the root e raised to power minus x minus mu whole square over 2 sigma square. So now let's identify the parameters here. So as I've told you, the parameters of a distribution can be simply identified by excluding the constants and the variable. So if you see here, if you exclude this constant and this variable, what is left is sigma and mu. So these are the two parameters. So we now complete the definition where the parameter mu can be any real number and the parameter sigma is greater than 0. This has to be the case because this mu is nothing but the mean of the distribution as well, and the sigma is the standard deviation of the distribution. So this standard deviation has to be greater than 0 and mean can be any real number. We also sometimes utilize the notation as, for example, x is n of mu comma sigma square. So in some of the books you can find this notation as well, and this simply means that x is a normal random variable, and normal is another word for this Gaussian random variable. So if you see some statement like this, it means x is a normal or a Gaussian random variable with these two parameters, mean mu and variance sigma square. This is an interesting distribution. This is a symmetric distribution, and its shape is something like this. Pardon my drawing, but this is the random variable x, and say this is the PDF. The total area under the curve is 1. Assume that this is a symmetric distribution, which means here lies the mean value, and you see the probability, all the probability below this mean value is exactly equal to all the probability above this mean value. We can have another Gaussian distribution, or the normal distribution, say something like this. Pardon my drawing, assuming that this is reasonably nicely drawn. So, if the symmetry is there, which obviously is there, this is the mean value. But now you see the spread of this distribution is greater than the spread of this distribution, which means that if you have the variance of this distribution and the variance of this distribution, the value of the variance of this distribution, or the standard deviation in other words, is greater than for this distribution. So, flatter the Gaussian distribution, the more the variance, and the more peaky the Gaussian distribution, the smaller the variance. Always remember that the area under the curve of any distribution, that includes the Gaussian distribution as well, the area under the curve, which means the integral of this distribution of this PDF, is always equal to 1. Finding the CDF of this distribution, which is continuous in nature and it starts from minus infinity and ideally reaches plus infinity to have the total area equal to 1. Finding the CDF is not an easy task, but the statisticians have calculated some tables, and we can use those tables to find the probabilities of certain meaningful intervals. So, I'll now show you how we can find probabilities of interests for this Gaussian distribution. Remember, Gaussian distribution occurs so normally, so frequently in nature, that it is also called normal distribution as well, and so sometimes we utilize this notation also. Now, I'll do an example and see how we can calculate the probabilities of interest or probabilities of certain intervals of interest if we have some Gaussian distribution available. First, recall the concept of standardized random variable. If you recall, I told you that the standard random variable is the one with zero mean and unit variance. The mean has been brought to 0 and the variance is brought to 1, just to make it some standard distribution. So, if we have a standard normal distribution, how we can find the probabilities of interest? I'll show you through an example. But before that, let me show you the table which generally the statisticians, the mathematicians use to find the probabilities of interest for the Gaussian distribution. So, this is a table of Gaussian distribution, standardized normal distribution. I have taken it from another book, so that they have used the term normal, but I have told you that the normal and Gaussian are one and the same thing. And let me show you, like this is the probability that the random variable z is greater than 0 and less than this. So, the total probability from 0 to x for a standard normal distribution. Standard normal distribution would mean like this. For example, here, this is the expression for Gaussian distribution, normal distribution, if we standardize this, it means that you have brought its mean equal to 0 and sigma equal to 1, and you know how to standardize a random variable. I'll do an example as well later on to recall that concept. So if you want to standardize this distribution, you simply put mean equal to 0 and sigma equal to 1. So if we put mean equal to 0, sigma equal to 1, this term becomes 1 over 2 pi under the root, and this term becomes e raised to power minus x minus 0 whole square divided by 2. So for this standardized random variable, statisticians have already calculated a table indicating the values of standardized random variable z. How to read this table is simple. This is the total probability from 0 till 1.51. So you take the you take this value and you take some of this value and you simply add them up. It will lead you to the total probability from 0 till that point for a standard Gaussian distribution. So for example, this is the probability 0.4838 is the probability, the total probability from 0 to 2.14. 2.14. So this is the probability, total probability, the cumulative probability, or the CDF in some sense, for the standard normal distribution from 0 till 2.14. So you simply add this and find the intersection, and this will give you the total probability in terms of CDF. So we will utilize this table, and if required, I'll provide you this table in the exam to find the meaningful probabilities. Unfortunately, the camera cannot focus it exactly, but we'll see how we can manage. Perhaps this one it will be better. Let me check. Yeah, it's more visible. So for example, this probability, let me see if something is available. Yeah, for example here. So this is the probability, the total probability of the Gaussian distribution from 0 till 0.5. This is the total probability from 0 till 0.53. 0.53. So this is the cumulative probability. 0.2019 is the total probability from 0 till 0.53 under a standardized Gaussian distribution. So we'll use this table to find certain probabilities of interest now. So suppose we have a standard random variable, already known that it is a standard random variable. Let x be a standard normal random variable. Use table and find first the probability that x is greater than 0 and less than 2. Second, the probability that x is greater than minus 2 and less than 0. Third, the probability that x is greater than minus 1.5 and less than 2, and D, the probability that x is greater than 1.14. So we need to find these 4 probabilities. The first one is so easy. You simply remember, this is already known that x is a standard random variable, which means we can use this particular table. I'll provide this table in the notes through our LMS. So the probability from 0 to 2 is exactly this one, 2.00. It is 0.4772. So this is already now calculated. This is 0.4772. Remember, the total probability is being calculated from 0 onwards, and we have already discussed that this is a standard random variable. It is symmetric, so only half of the interval is used. The rest of the other half, the rest of the distribution, which is the other half, is automatically known. So you see the total probability going from 0 to infinity will be just 0.5. The remaining 0.5 is on the other side of the distribution. So this table is effectively for a distribution something like this, where mean is equal to 0, and we are calculating through this table. We are basically using this part of the probability, and if we know this part of the probability, because of the symmetry, this part is automatically known. So the CDF from 0 to 2 basically means, say if this is 2, the total probability in this interval. So if we know this total probability which we have just computed, it is 0.4772. because of the symmetry, we automatically know that from -2 to 0 it is exactly the same. So now the probability from 0 to 2 is 0.4772. The probability from -2 to 0 because of symmetry is also 0.4772. So you see the strength of the symmetry. Only half of the probabilities are calculated, and the rest half is automatically known because of the symmetry. Coming further, what is the probability that x is within this interval? So we can always write it as the probability that x is greater than -1.5 and less than 0, plus probability that x is greater than 0 and less than 2. And you can always write it as probability that x is greater than 0 and less than 1.5 plus 1.5. You see this one, 0 to 2 is exactly equal to -2 to 0 because of symmetry. So between -1.5 to 0 is exactly equal to the probability 0 to 1.5. So I can write it as probability that x is greater than 0 and less than 1.5, and plus the probability that x is greater than 0 and less than 2. So if you use the table, you will see that the probability, this probability is already known. This is 0.4772, but what about 0 to 1.5? So which means this point, and this is 0.4332. Hopefully it is visible. The probability is 0.4332, so I write it as 0.4332. So it ultimately becomes 0.9104. I leave this part as homework. Please note that it is asking for the probability greater than 1.14, and you know the total probability from 0 till infinity is 0.5. From 0 till infinity under a standard Gaussian distribution is 0.5. So what about the total probability from 1.14 onwards? So you have to utilize this part of the probability distribution, which is 0.5, automatically known. So from this 0.5 total probability, you have to somehow use your brain and in today's lecture to find the probability that x is greater than 1.14. So this is a homework. You must solve this to strengthen your concepts about Gaussian distribution. I move on to the last part of today's lecture and discuss how we can find the probabilities of non-standard random variables, non-standard Gaussian random variables through the standardized random variable. So if a variable is non-standard Gaussian one, we can simply make it a standard Gaussian one. You already know that a standard random variable has zero mean and unit variance. So if you have a non-standard random variable, you can make it a standard random variable through certain transformation, and you know what is that transformation. So if suppose x is a normal random variable with parameters mu and sigma square, and this is say non-standard random variable Gaussian one, you can always make it a standard random variable z by simply subtracting the mean and scaling it with 1 over sigma. If you do this, the mean of this will become 0 and the variance will become 1, and so you will call this as standard random variable. So now if you want to find the probability that this non-standard random variable x has a probability, total probability in this interval, you can simply first convert it into a standardized form. Standardized form means all the range to be converted into standardized form, which means you need to find you need to transform the random variable x, the non-standard standard random variable x as such, and so you transform the endpoints, which is a, you subtract the mean and you scale it with 1 over sigma, and similarly the other endpoint, which is b, minus the mean over sigma. So now this basically becomes probability that z, this is now standard, z greater than a minus mu over sigma and less than b minus mu over sigma. So if this is the case, we can quickly now move on to solve an example, the final example of today's lecture. So example, suppose x be a normal random variable. Normal means Gaussian random variable with parameters mu equal to 2 and say sigma equal to 0.5. We need to find the probability that x is greater than 1 and less than 2.1. So how can we find this probability? The table available is for a standard random variable, but you see here that this x is a non-standard random variable. Why? Because mean is not 0 and sigma is not 1. So first we need to convert this x into a standard Gaussian random variable, standard normal random variable, which means you need to find the probability that x is greater than 1 and less than 2.1 by transforming x to a standardized form, which means x minus mu over sigma, and then obviously the endpoints also need to be transformed, which is 1 minus mu over sigma and less than 2.1 minus mu over sigma. So now this becomes easy. You need to find the probability. X minus mu over sigma is z, which is basically the standardized form of this, and the endpoints of the interval are also standardized as such. 1 minus mu, which is 2, over sigma, which is 0.5, and less than 2.1 minus mu over sigma, which is 0.5. So now this becomes easy. Probability that z is greater than minus 2 and less than 0.2. So now you can break it into two parts. This is the probability that z is greater than minus 2 and less than 0, plus probability that z is greater than 0 and less than 0.2. So you write it as probability that z is greater than 0 and less than 2. This part can be written as this because of symmetry, and this is already in the 0 to infinity range. So now use the table for this value, use the table for this range, and you will find the probability. So if I check it from 0 to 2, we already know that this is 0.4772. Even if it is not visible, just trust me. So this part of probability is 0.4772, and this part from 0 to 0.2 is 0.0793. So the total probability becomes 0.5565. So this is how we can find the probabilities of a non-standard probabilities of interest for non-standardized random variables using the standardized tables. Now a quick revision of what we discussed in today's lecture. This was lecture number 1 for week number 13 of the course Probability Methods in Engineering, EE-251, for all the sections A, B, C. We just discussed one family of continuous random variables, and this is the most important and most normally occurring of the families, Gaussian random variable. This is so normal that this is also denoted by capital N, and if somewhere if you come across with this expression or some expression like this, it means x is normal or x is a Gaussian random variable with these parameters mu, which is the mean, and sigma square, which is the variance. This is the expression. We do not need to worry about how it was derived. This is the expression of Gaussian PDF. The parameters mu and sigma are basically the mean and standard deviation. So the sigma square is the variance. This Gaussian distribution is always symmetric about the mean value. The total area under any PDF, and it includes Gaussian distribution as well, is always equal to 1, and this is how you calculate it. So and you see the symmetry property of this distribution. Symmetry property says that the mean is exactly in the middle of the range of values. So the statistician have only calculated half of the probabilities, and the remaining half is automatic. One more point: if the distribution is peaky, it means variance is smaller. If the distribution is flatter, it means variance is larger. And using the symmetry property, we can find the probabilities in any interval using the table that I had shown you. Because of symmetry, if you know the total probability from 0 to 2, you automatically know the probability from -2 to 0, because this is exactly the same probability. So we discussed how to calculate the probabilities of meaningful intervals using the table, and we did this example where we solved these 3 parts, and I left this part as homework for you guys. You must think about this. This will increase your understanding of the Gaussian distribution, and how and understanding on how to utilize the table. And then we saw how we can create a standard random variable from a non-standard random variable by simply subtracting the mean and scaling it with 1 over sigma, and then for any range you can simply standardize all that range by converting this x, transforming this x as such, making it standardized one, and doing the same procedure with the endpoints of your interest, A and B. So now this is in the standard form. Then we did an example where we had a normal random variable, a non-standard normal random variable x, and we had to find the probability that x is between 1 and 2.1. And this x is a non-standard normal, non-standard Gaussian random variable. How we know that this is a non-standard one? Because its mean is not 0, its sigma is not equal to 1. So first we need to convert it into standardized form, which means x has to be converted through this transformation, and obviously then the endpoints as well. So if we apply this, we get this expression, and so we get this range. And now you have converted this x into z, which is a standard Gaussian random variable, so its table is available. So we have utilized the table by converting this range into 2 meaningful interval. Remember, we have just 0 onwards probabilities available, only 0.5 of the total probability available through the table. The rest can be automatically calculated using the symmetry property. So from -2 to 0, and then from 0 to 0.2. And this -2 to 0 is exactly the same as the probability from 0 to 2. And this is again known through the table. So we utilize the table, find these 2 values, and then we get the total probability that x is from 1 to 2.1. So this is the total probability. Thank you very much, dear students. We have covered much of chapter number 4 about single continuous random variable. Only one more topic is left, and then we'll be done with chapter number 4. Mr. Zevar Ali, the other instructor of the course, will give you assignment from this chapter at an appropriate time. Thank you very much for your attention.